Okay, so in the previous video, I told you that the definition, this was a definition, that the definition of the, this is the Christoffel symbol of the second kind, Christoffel symbol, we'll just call it, was equal to this, and we derived how this this term here, which we're going to call the Christoffel symbol, is very important in the geodesic equation. So in this video, what I'm going to show you is how we can rewrite this bit in terms of the metric tensor, derivatives of the metric tensor. So we're not going to rewrite this bit because this bit's already in terms of the metric tensor. We're given the metric tensor field, remember. We're not given these y coordinate systems, which remember are the locally Euclidean coordinate system, or in the case of a flat space, the globally Euclidean coordinate system, the coordinate system with the Euclidean metric at that point. Okay, and remember, in principle we can calculate these, but in practice we don't want to calculate these. We can calculate them in principle from the metric tensor field. Okay, so go back to the definition of the metric tensor. The metric tensor of our manifold in our coordinate system x is given by, oh, I'm so sorry for it blurring in and out continuously. Microsoft LiveCam, absolutely terrible piece of kit. Anyway, so the metric tensor is given by convert the vector into convert both, because remember we're going to contract it with both vectors. So convert both vectors into the y coordinate system, into the locally into the coordinate system with the locally Euclidean metric, and then basically all you do is you are going to contract these in the Euclidean fashion, i.e. Pythagoras' theorem. So that is our metric tensor. So we would write this in our nice neat notation: yn differentiated with respect to I, yn differentiated with respect to j. Now what we're going to ask is what happens if we differentiate the metric tensor with respect to, let's say, r, gij. What do we get? Well, we're going to use the product rule, so we'll get yn I r yn and this just means differentiate with respect to I and then differentiate with respect to r. So it's that if I wrote this out in full, it would be d2y n dx I dx r. In fact, it would be the other way around, but of course they commute. Well, providing, yeah, they in general relativity, in classical general relativity, these certainly commute. Plus yn differentiated with respect to I, yn differentiated with respect to j, r. There. So this is our expression. Now what we're going to do is we're simply going to cycle these indices. You can't stop me from doing that. I'm just going to relabel r as j, I'm going to relabel I as r, and relabel j as I. You can't stop me from doing that. These are just indexes, they're meaningless. So I'm going to do j, g, r, I. So I'm going to cycle them. So all we do is we turn i's into, what have they become? They become r's. We turn j's into i's, and we turn r's into j's. Okay, so n can remain the same because it's just a dummy index. I goes to r goes to j, yn j goes to I, plus yn I goes to r, yn. This may seem slightly unmotivated, but you're going to see why it's so important in a moment. All you need to appreciate is that you can't stop me from doing that. There's nothing wrong with me doing that, even though the motivation might not be clear. You're going to see the motivation in a moment. So now we're going to cycle them once more. We're going to take r to here. J is going to become, I is going to become j, and r is going to become, what will it become? I. So di j, g, I goes to there, r goes to here, j goes to here, j, r. Okay, so yn differentiated with respect to I has become r, r has become, wait, what have I done? No, I has become j, r has become I, yn, j has become r, plus yn, what have we got here? I has become j, yn, j has become r, and r has become I. Okay, so now we've got all that we need to actually derive this. So what we're going to do, what we want is we want something that reflects this, and unfortunately I haven't used the same indexes, which is just really annoying, but never mind. We're going to, we can take any of these two, because these commute, these G or Y differentiated with respect to J R is the same as RJ, so these two you can swap them around. Basically, that's just I've forgotten it's like Chatter's law or something. No, I shouldn't say that. It's some law from multivariable calculus. It's very easy to prove that if you just go around in a square, they don't. In fact, shall we prove it? Yeah, let's just do it really quickly. In multivariable calculus, imagine we've got some surface z as a function of x and y, and we want to examine a little square of this surface. So we've got our little dx, we've got dy, and of course coming out of the page will be a dz. So for a change in x, how much does z change? It changes by del z del x dx. How much does it change for a change in y? Del z del y dy. So the z at this point, let's call the z at this point z. So the z at this point will be z plus this, and the z at this point will be z plus this. And basically what we want to happen is we want that if we add the bit along here and get to here, then it's the same as if we go along this way, get over to here, and then add the bit on here. So what do we add if we go along here? Well, we add the same as this, but we also add how much this has changed for a change in y. So del z del x dx, but the dx is obviously a constant, so that can be pulled out, dy, and that's how much this overall is how much you need to add on at this point. So what we're saying is that you change it for the same amount as here, and you have to add on however much it's changed, because the change that you endure if you go through this has changed because it's changed in y, and this is how much it's changed because you've changed in y. Okay, so if we add that to this, because that will be the total amount of dz, we get this. So one way we get del z del y dy plus del z del x dx plus the second derivative of z del y del x dx dy. And that's the final answer here. That's the way if you go around that way, and now we want to get the same answer if you go this way. So we want that to equal, so we've got this bit, that's this, del z del x dx, and of course on both sides you'll really have plus z, but the plus z will cancel. Plus, how much does this change? Well, it changes by del z del y dy, but plus the amount that has changed because you've endured a change in x. So del x del z del y dy, and times that by the little change in x. So cancel that, cancel that, cancel that, cancel that, cancel the dx dy, and you get that d2z dy dx is equal to d2z dx dy. Okay, so that's a little proof of that these two commute, basically. Otherwise, you don't. Basically, you can go around one way and you'll get you won't be on the surface. The surface doesn't make any sense if that isn't true. Okay, so back to what the theme of this video, which was, in fact, I'll cut the video here and we'll do the rest in the